remember, the problem we were discussing in the last class was the computation of derivatives numerically, the numerical computation of derivatives given a set of data points. That is, you have given a set of data points which is coming from some other calculation or from an experiment. So, you given by some other functions, you had a set of data points, and you want to compute derivatives in between or on any of these data points. So, you may want to evaluate the derivative of this at somewhere in between, or even on one of the tabulated data points. So, we are discussing cases where there is only one dimensional a function of one variable, and so the one way we said that in which we can compute this derivative is by constructing a polynomial which interpolates these points, okay, and then take the derivative of that polynomial. And then we looked at what will be the error in the polynomial, error in the derivative, because it is easy to compute it this way, because we know that the error in an interpolating polynomial is like the next term in the polynomial. So, the error in the derivative would be the error in the next term, and that is what we looked at in the last class. Okay, so, to summarize, we said that we could, if given a set of data points, we know how to construct a polynomial of order n which passes through this n plus 1 points, and starting from x0 to xn. So, we n plus 1 points, and we know how to construct this polynomial. And the advantage of writing it in this kind of Newton's form is that what is called the Newton's form for the polynomial is that these coefficients of these terms, that is f of x0 x1, f x0 x1 x2, these are coefficients of the polynomial of the terms of order 1, 2, etc., can be constructed rather easily from a difference table. So, that it's algorithmically efficient way of doing it. So, it is that this is a useful form for the polynomial to construct the derivatives, and that is what we looked at in the last class. So, then we said that the derivatives of this polynomial, now then once we have the polynomial of that form, then the derivatives can be written in this fashion. So, look at that, this is a second order term. So, we had the first order term now. So, the derivative of this, so now this does not appear in the derivative being a constant, and here this is the first term, and the derivative would be just f of x0 x1, right, and the next term would be f of x0 x1 x2 with the first order term, that will be x minus x0 plus x minus x1. So, that is the term, and then we have the error term, the last term being this, and then we have an error term which we can evaluate, because we know this term is a derivative of the next term in the polynomial, that is the n plus 1th term in the polynomial. That is what this error term is. Okay, so, that can be evaluated. So, we get that as this one, that is some function. So, we get that as something of the order of n plus 1, there is some derivative of the order of n plus 1 of some function, and multiplied by xi minus xj, a product of xi minus xj for all j values which is not equal to I. So, now this form is valid, actually strictly valid only when the error is evaluated at one of the tabulated points, and if you want to evaluate the error at a non tabulated point, then we have one more term which is actually this term multiplied by the derivative of this function, which we said is difficult to evaluate or impossible to evaluate, in the sense because we do not know what the functional form of this is. Okay, so, basically this form of the error will give us only a qualitative idea about what the error is, and most of the cases we will not be able to say what this term actually, or the order of the magnitude of this term is. We can only say that it is of the order of n plus 1th derivative. But we saw that if you have a set of data points, and in between we saw that if you have a set of data points like this, okay, so let us say we have many data points, and you want to compute a derivative here at any point in between. Let us say we want to compute the derivative at this value of x, and then it is not necessary to take the whole polynomial which goes through the whole data set of data points. So, we could actually construct a polynomial here which goes through these 3 points and then take the derivative here. Okay. So, this way we can actually get an exact measure of the error, because we can actually take this polynomial, this point also, and construct another polynomial, okay, which goes through all of this 4 points, right, and then look at the derivative coming from that. So, the difference between the polynomial which goes through these 3 points, okay, let us call that as P3 of x, okay, and the polynomial which goes through, this will be P2 of x, 3 points of order 2, and the polynomial which goes through 4 points, which will give us P4 of x. Now, you take the derivative of these 2, and the difference between these 2 derivatives evaluated at this point will give us an error in the this again is P3, and the error in the derivative P2, because the error in the polynomial P2 is like the next term which we can get from the P3. So, that is what we looked at, and we found that this gives us a very good approximation, a very good idea about what the error in the derivatives are. So, that was the case with the Newton's form of the polynomial, okay, that is polynomial of using a polynomial of this form, okay, and then take the derivative of this. And you remember what this f of x0 x1 was. So, okay, so then we could construct some set of data points, we will call them I1, 2, 3, 4, 5, etc. And then we had the xi values, which is now x0, x1, x2, x3, x4, x5, and then we had the f of xi values. Okay, so that was given here as f of x0, f of x1, f of x2, okay, so now this was given to us in the form of a tabulated set of data, and then we could construct these coefficients as f of xi's, right, as f of xi's are basically this point itself. So, that is the same as f of x0, f of x1, f of x2, f of x3, f of x4, f of x5. So, that is f of xi, and then we had f of xi plus 1. That is the next term in the thing, and which we said is given by f of x1 minus f of x0 divided by x1 minus x0, and f of x2 minus f of x1 divided by x2 minus x1, and f of x3 minus f of x2 divided by x3 minus x2, and we had f of x4 minus f of x3 divided by x4 minus x3, and the last term would be f of x5 minus f of x4 divided by x5 minus x4. So, we could construct that. Okay. So, that is the difference table which we constructed, and then we could take the next one would be then the difference between these two divided by, so this term would be now, since to simplify it, I will just write this as, remember, this is f of x0 x1 and this is f of x1 x2. So, the next term would be f of x2 x1 minus f of f, this is square brackets, remember this is distinguished between the square brackets in this bracket, x1 x0 divided by now x2 minus x0, and here the next would be f of, so this will be x3 x2 minus f x2 x1 by x3 minus x1, and here you will have the next term would be f x4 x3 minus f x3 x2 divided by x4 minus x2, and the last here be f x5 x4 minus f x4 x3 divided by x5 x3. Now we can construct further. Okay, now taking the difference between these two, and then it will be the denominator will be x3, in this case would be x3 minus x0, and it goes further like that. Okay, so the next term will have a denominator x3 minus x0 here, and here you'll have x4 minus x1, you'll have x4 x5 minus x2, and you can construct a difference table of this form. So that's what we had. So these two went to that, and then so we had a difference table constructed in this fashion. Okay, now these two will go to that, and this, and we had these two going to that. Okay. So this difference table is what gives the advantage in this particular case, that once we have the difference table, and whether it is a polynomial or it is derivative, we can write that in terms of these coefficients by reading off these coefficients. Okay, now if I am entering the difference table at this point, that is, I am entering the difference table at the top, okay, and then I have the coefficient. The first term would be just f of xi, which is f of x0, and the coefficient of the next term would be f of x1 x0, and then f of x2 x1 minus f of x1 x0 by x2 minus x0, and then down that way. Okay. So that is what we have written as this term here. So this is actually entering the difference table at the top. But I said that if we want to evaluate a derivative at any point in between, there is no need to enter the difference table from the top. We could enter the difference table somewhere in between. Okay, what I mean by that is, if I want to evaluate the derivative of if I want to get the derivative of the function at some value x, where x is, let's say, larger than some xi. Okay, so xi is the larger than xi, and then I could actually enter the difference table at that point xi. So let me say that's this point in this case, okay, and construct a polynomial this way, or around that, or maybe I could enter here and construct a polynomial that way. So I could enter the difference table in principle anywhere, okay, which contains this point x, such that it contains this point x. Right. So in this case, I could construct, so here I had 5 points, so 1, 2, 3, 4, 5, let's say, we had 5 points, and I want to construct a derivative of this point here, evaluate the derivative at this here. So I could use a linear polynomial by just taking 2 points. Right. I could just take construct a linear polynomial, and the derivative of that will be constant. Okay, so that linear polynomial I could construct by entering into the difference table at this point. That's the third point. Okay, that is 0, 1, 2 here. Okay, I would enter here, and then my polynomial would start from f of x2. Okay. So then my polynomial will be f of x2 plus f of x3 minus f of x2 by x3 minus x2 into x minus x2. Okay. So that's the way of that's what we saw yesterday. Okay. So that's the way of constructing that polynomial and the derivative. Okay. So if I want it here, okay, that is x0, x1, x2. So in between x2 and x3, I want to find the derivative. Okay, and I decide to take a linear polynomial between which connects these 2 points. That's a straight line, and that I would construct as, so p of x as now f of x2. That is my first term in the polynomial. That is f of x2. It will be. So I'm entering here. Okay, and then that's entering here, so that's the first term, f of x2, and the next term would be f of x3 plus f of x3 minus f of x2 divided by x3 minus x2 into x minus x2. Okay, so that will be my that's my polynomial. Okay, so it's f of p of x is f of x2 plus f of x3 minus f of x2 by x3 minus x2, because this is my coefficient x2 x3, okay, which comes in here. Okay, and that's my polynomial, and then I can take the derivative of that, which would be simply f of x3 minus f of x2 by x3 minus x2, which is actually a straight line connecting this, the slope of this line. Right. So that's the way I can construct this. Okay, so now, so we need a notation for that. So we normally write it as, you know, what we call it as pi of x. Okay, pi of x we'll have to denote here, or when we write this difference table, we'll have to put an I, just to say that where at which point in the difference table are we entering. So now I can construct the same derivative here. Okay, evaluate the same derivative here by constructing a second order polynomial. Okay, so now this is a first order polynomial. I could construct a second order polynomial, but then there are two ways of doing it. I could enter the difference table here, okay, and write the next term to this polynomial. Okay, now this is linear. The next term would be taking this coefficient. Okay, the first term is this. I entered here. Okay, so I enter at this point. Okay, this point is where I enter. Okay, so I have the first term this, second term this, and that is the second term was this is a linear coefficient of a linear term, and this will be the coefficient of the quadratic term. So that will be f of x4 minus f x4 x3 minus f x2 x3 divided by x4 minus x2 into x minus x2 into x minus x3. So that will be the next term. That's one way of doing it. Or I could say that I would enter here. Okay, so that I will enter at this point. Okay, and then construct a polynomial which goes up to that. That also gives me a second order polynomial. So then I would enter here, and then my term would be f of x1 plus f of x2 minus f of x1 by x2 minus x1 into x minus x1 now, because I entered at x1. Okay, and then the next term, which will be x minus x1 into x minus x2. So there are two ways, or there are many ways now, right? So now if you're constructing only linear polynomial, there is only one point where we can enter to construct the polynomial. But if you are doing a second order polynomial, that's quadratic polynomial, then there are two ways we can enter, either here or here. Okay. Now we can see that the possibility goes up if we are constructing a higher order polynomial to evaluate the derivative. Okay. But the major point which I wanted to say is that you have to remember which point in the difference table you enter, and you should keep that in mind when you construct this, when you make the algorithm. So we will see the implementations of this algorithm in later class. Okay, so that's now the Newton's form with x0, x1, x2, x3 tabulated on a difference table. So now the distance between the difference x0 minus x1, x1 minus x0, x2 minus x1, x3 minus x2, etc. could be very different. There is no need of them. There is no need of, in this particular form, there is no need to restrain that differences. But there could be any value. But we have seen earlier in our interpolation, when we were looking at the interpolation case, that its advantages or the algorithm gets much simpler when you look at tabulated points at equal distance. That is, x1 minus x0 equal to x2 minus x1 equal to x3 minus x2 equal to some value h. So in that case, even obviously the whole algorithm is much simpler, okay, and the polynomial is much easier, and so similar reasons, we'll also have the derivative to be much simpler. Okay, so now we look at this case where we have derivatives from evenly spaced data, that is, all the data points xi plus 1 minus xi are at equal distance. Okay, that is, all the xi points are at equal distance, and we call that distance as h. So h is the distance between any two data points of this evenly spaced data, and we will do this thing with a specific example of a function f of x equal to e to the power of x, whose derivative we know very well. So what we can do is we can take this function, okay, and evaluate it at some equidistant values, okay, and construct a difference table, okay, and then we will calculate the derivatives from that, and then see what the error is, and etc., like we did in the other in Newton's form earlier. We will do the similar procedure here again. Okay. So now in this case, as I said that this difference table is a little simpler, that is, since x1 minus x0 is equal to x2 minus x1 is equal to x3 minus x2, there is no need to keep those things here. Right? We don't need to differentiate that here, or we do not need to divide the things here. So we can actually remove those points from here. Okay. So because we know that's a constant. So irrespective of which point in the thing we enter, that's a constant. So we don't need to keep that here. And similarly here, x2 minus x0 is now 2h. So we are going to write for the evenly spaced data. We are going to say that xi plus 1 minus xi is equal to h. That's what we are going to use. Okay, so all this becomes some h, and this will become 2h, etc. So we don't need this also. So as we can see, the difference table will become simpler, right? And then we have to distinguish between these functions which we obtained from the Newton's form for unequally distributed data to this. To distinguish between these two, we change the notation here a little bit. We call this as delta now. Okay, so we call it as this has become del 2, etc., and this is now delta. So that's the notation we would use. So in the next term, so this will be del 2. Okay. So we have delta, and we have del 2, and then we have del 3, and we will continue with that. Okay. So that's what we would be. That's the notation which we are going to use. Okay. And then the difference table for the data which we obtained from this would look like the following. Okay, so now we have what's called delta f, del square f, del 3f, del 4f, del 5f, del 6f, etc. Okay, as you go along. Okay, so the notation we are going to just simply use f. Okay, so that's what we will have. Okay, so sorry, I just made a small mistake. It should be delta f here and del 2f here, and that's just a function f itself. Okay, so the difference in the function called delta f, and the difference on the difference is called del squared f, etc. Okay, and so that's the coefficients which we will have. Okay, in this construction. So this is just evaluated at equidistance, that is h in this case is 0.6, as you can see. So 1.3, 1.9, etc. And we evaluate the function which is e to the power of x. We know the functional form, but let's say we don't know the functional form, then we have some set of data points given at that x values. Then we construct the difference table as just taking the difference between these 2 points as this one and these 2 points as that here, and the further difference further differences are represented as del to the power del n f in general. Okay. So now again notice this I have put in here, del fi here. Okay, now this is to again denote that which point on the difference table which we enter. Okay. So this is the general notation. So if we enter, as I said earlier, that if we enter the difference table at 2, we will be calling that as delta f2, del square f2, del 3 f2, del 4 f2, etc. And if you enter at 3, and then we construct the polynomial this way. Okay, so this is the way we will construct the coefficient of the polynomial will go in this fashion. So that will be called del 3 f and del 3 square f and del 3 4 f, etc. If you enter here, okay, that's where it will go. Okay. So that's the table. We'll come back to this table again. We need to look at this table when we actually do the example. Okay. So now the question is, what's the form of the polynomial now? The form of this polynomial function, obviously we have taken out the denominators from these points to write as del f. So del f is related to the coefficients of the Newton's form by saying that f of x1, x2, x1, x0 here, for example, f of x1, x0 will be del f1, del f0 divided by h, right. So we will have this kind of form, f of x1 or x0, x1 will be now del f. Now we entered this at 0, so del f 0 divided by h. Okay. So that's what we have to divide this by h to get that coefficient in the polynomial. So in general, the formula is this. If you go to higher order terms, okay, in general the formula is, we have seen this earlier in the case when we are doing the polynomial interpolation, that I'm just repeating those things here. So that is the coefficient of the nth order term and nth order term would be then del n fi divided by n factorial into h to the power of n. Okay, again, this will denote the point at which we enter the data point. So del fi says the difference between xi plus 1 minus xi. Okay, remember that it's xi plus 1 minus xi is what I is. Del fi here is. Okay. Okay, so now we will define a new variable, that is s, we call it s, which is x minus xi by h. Now let's say we want to, what do we want to evaluate? We want to evaluate derivatives or the polynomial at any point x. Okay. So then what's now the terms, then the polynomial would be x minus x0 and x minus x0 and x minus x1, etc. Right? So that's what the terms in the polynomial was. We had it before. Okay. Remember that the polynomial in the Newton's form was Pn of x would be written as, so we said f of x0 plus f of x0 x1. This is the coefficient, and then this is x minus x0 other terms. Okay. Now in the new notation, this would just go as f of f x0 plus, now we have a del here, sorry, a del f, right, divided by h, we say, and then x minus x0, okay, plus other terms. So now since this is a h is a constant, okay, now we can define a new variable instead of writing x minus x0, x minus x1, etc. And we can define a new variable, and that variable which we define as x minus x0 by h, because we entered here at 0. So this is del 0, sorry, del f 0, because we are entering at 0. So this is, so this is one way of writing it. So we can define x minus x0 by h as one variable. Okay. But in general, if you enter at any point I, okay, and we construct a polynomial from that, okay, so then we will write the polynomial as of order nth order polynomial as we'll say fi at x0, right. So that is the f at f xi, okay, that is the value at which I enter at some point, let's say x2 here, that is f x2, and then we will have here del f2 del fi divided by h, right, into x minus xi as the first term, and then we'll have next term as, remember, it will be del 2 fi. Okay, now you will have an h squared coming there, okay, because of two terms. Sorry, it will be 2h. So it will be h squared into 2. That's what you will get as the coefficient. Okay, and then you will get it as x squared, x minus xi into x minus xi plus 1. Okay, and then there will be other terms. Okay, so then higher order terms in this case. Okay. So now what we are saying is that, but x minus xi plus 1 is, we know that xi plus 1 minus xi is h, right. So we can write xi plus 1 as xi plus 1 can now be written as h plus xi. And we can substitute that here. So you get x minus xi plus h. Okay, so we can write everything in terms of x minus xi, okay, because all these are equidistant. So we can write everything in terms of xi, and write it in a simple form. We define a new variable which is x minus xi divided by h as s. Okay, so we define this new variable x minus xi divided by h as s, which we saw in the equidistant form in the polynomial interpolation. And now with that, we can write all the terms in terms of s. For example, just I said x minus xi into x minus xi plus 1. Okay, that term would become x minus xi. We know is that, and then xi plus 1 now we write as xi plus h. So that is xi plus 1. So I can write this as x minus xi into x minus xi minus h. Okay. Or that is, if I write it in terms of this variable, it will be just h square into s minus s into s minus 1. Okay. So the advantages, you remember that, you notice that when you put it in here in this coefficient, okay, in this coefficient and multiply it by this coefficient, these terms would get cancelled and we will only have a n factorial in the denominator. Okay, so in the form, then we will have the polynomial which is of this form. The interpolating polynomial will now simply have this particular form. Okay. So nth order polynomial where we enter at I, right? So we enter I in the difference table. So we have f of I fi plus s into del fi plus s into s minus 1 by 2 factorial del fi del 2 fi and s into s minus 1 into s minus 2 by 3 factorial del 3 fi, etc. So that's the advantage. Okay. So when you have equidistant points in the or the data points given are equidistant, and then the whole thing simplifies to a polynomial of that form. Okay. So now the new polynomial which we write would be, we'll keep that in here. So we'll write the polynomial as Pn of x as fi. So that's where we enter into this, okay, 2 or 3 or wherever we enter in this, plus then we say s into, so we have s into delta fi plus s into s minus 1 by 2 into del 2 fi plus s into s minus 1 into s minus 2 divided by 3 into del 3 fi. Okay, so that's the form which we get, and we remember what del 1 fi del 2 fi are given by this. Okay, I to note that where we start. Okay, so if you start from here, it is called 2. If you start from here, it is I is 3, etc. Okay, the last term would be then a product of s minus j, where j goes from 0 to n minus 1, or delta to the power of n f by n factorial, and the next term is again the n plus 1th term, that is the error in the polynomial. Okay, so now the derivative of this polynomial can easily be written, right. So once we have this form, we can write the derivative. Remember, s is x minus xi by h, right. So the derivative with respect to x of this is derivative with respect to s into ds by dx. So we will write p d by dx of Pn of x as d by ds of Pn of x into ds by dx. Okay, that's what you're going to do. So then ds by dx is just 1 over h. Okay, ds by dx 1 over h. So it becomes 1 over h into d by ds of Pn of x, and we know what Pn of x is. We can take the derivative of that. So this will be simply, this will be, so that it will start with del fi, that will be the first term. Okay, so it's a 1 over h. So 1 over h into del fi, that's the first term, and the second term would be, as you can see, is s minus 1 plus s, right. So s minus 1 plus s by 2 is one second term into del 2 fi, etc. So that's what we will get. Okay. So s plus s minus 1, that is that's what I have written here. The whole term is written here. Okay. So the ds by dx will just give us a 1 over h. Okay, and the first term would be del fi, delta fi, and the second term would be s plus s minus 1 by 2 factorial into del 2 fi, etc. Okay, that's what we are getting. Right. So this is basically what we would have as a polynomial, as a derivative. Right. So now we can evaluate this derivative at any value x you want. Okay. Once you given x, you can compute s, and then we can use that to get. Okay. So the error is again the derivative of the next term in the polynomial is our error here. So we can apply this to the specific problem which we were looking at, that is the case which are e to the power of x. Okay. So, we have tabulated there for e to the power of x function. So, and we had a set of this, and we can use this difference table and then look at a particular example of this implementation of this. Okay. So, again emphasizing this point again, this I which we use here, okay, is the is to denote where we enter the difference table. Okay, so now if we go back, so let's say we want to evaluate the derivative at x equal to 3.9. So, okay, then x equal to 3.9. So, let us go back and then look at the difference table. Okay, so, we had the difference table here. Okay. So, if you want to evaluate the derivative of the function at 3.9, okay, so we could enter here. Okay, 3.9 is between 4 and 5. So, I could just enter here, okay, and then say that I will have the difference. So I will construct a linear polynomial, okay, the linear polynomial between 4 and 5. So, I have to enter at least at 4. So, the first thing I can do is construct a linear polynomial between 4 and 5. Okay, so, that is saying that I will have a term only terms up to this, right. That is what I would be saying. Okay. So, in the derivative and in the polynomial I will have terms up to the linear polynomial means I will have only these two terms. Okay. And I am entering at 4. Okay. So, when I enter at 4, okay, so I enter at 4, so I will have f of x4 and f of xy minus f of x4 as the delta f4. Delta f4 would be f of x5 minus f of x4. So, that is what I would be, and then s would be x minus x4 divided by h. Okay, h in this case is 0.6. Okay, that is what we will have. So, we can enter here and then construct my polynomial. Okay, so I will construct my polynomial. The first term in the polynomial will be 40.447. Okay, and the next term would be 33.253. So, that is what the delta fi is into s. So, what is s in this case is we want to construct at 3.9. Okay, so s is if you want to do this at 3.9, so at x equal to 3.9, s will be equal to 3.9 divided minus. So, our xi is 3.7, so it is 0.2 divided by 0.6. That's what we, or 1 by 3. That's what we have as s. Okay. So, we can construct that polynomial from this. So, if you note down this, then it's easy that we enter here. Okay, and the first term in the will be 40.447. Next term would be s into delta fi. S is 1 by 3. So, 1 by 3 into 33.253. That is our polynomial. Okay. So, that is our linear polynomial. Okay. So, the linear polynomial is going to be in this particular case is so now we have x at 3.9. Okay, and we are entering at 4. So, x4 is 3.7. Okay, so, s is 1 by 3 and the polynomial which we have is order 1 polynomial would be f of x4. So, we have f of x4 plus 1 by 3 into delta f4. So, that turns out to be what we see here as 40.447 plus 33.253. So, 1 by 3, 33.253. Okay. So, that will be the value evaluated at of p of x. Okay, because now everything is number here. So, this is at x equal to x equal to 3.7. Okay. So, p at x equal to 3.7 we can evaluate that. So, we do that, or if the polynomial at p of x entering at that would be just f of x4 is 40.447 plus s by s into 33.253, and the derivative of that polynomial which we know is 1 over h into dp by ds, okay, and that is simply 1 over s by, so 1 over h into 33.253. Okay, that is what we have. So, that is what we will get, we will see that here. Okay, so, we could evaluate that, etc., 33.253 by 0.6. So that h is 0.6, so it is 33.253 by 0.6. So that will be the, and then the error term. So what's the error in this term? Okay, so that's the next term in the polynomial, as I said. Okay, so next term in the polynomial would be s into s minus 1 by 2 into del 2f high, del 2f4 in this case. Okay, so that's the next term in the polynomial, and so the derivative of that would be s minus 1 plus s by 2 into del 2f5 into 1 over h. Okay, so that's the derivative, that's the error. Okay, so we know that this value, that is 33.253 by 0.6, is not the correct derivative. Means e to the power of x derivative is e to the power of x. So e to the power of 3.9 is not 33.253 by 0.6. It's off by 7. So there is definitely approximately off by 7. So this is definitely wrong. Okay, because we have just constructed a linear polynomial. So let's look at the error in this, and the error would be the next term in the polynomial. And I said the next term in the polynomial is this one. So we have so far taken only this. The next term would be that term. Okay, or the derivative of that with respect to x is 1 over h times s minus 1 plus s, or 2s minus 1 by 2 into del 2f5. And we know all that thing. We know what del 2f5 is, right? So del 2f5 from the, that is del 2f4. Okay, so that is starting from 4. Del 2 is 27.337. Okay, so the error term, okay, the error term which I call E, is then 1 over h, okay, into 2s minus 1 by, so error here is 1 over h into 2s minus 1 by 2, right? That's what we have, 2s minus 1 2 into del 2 f4. Okay, that's the error in the term. Okay, so del 2 f4 is see again f4 means I start from 4. I look at del 2. So starting from 4, del 2 is 27.337. Okay, and s we know is 1 by 3. Okay, so we can evaluate this quantity. Okay, and write the error in this particular example case as okay, as 27.337 by 0.6, that is 1 over h, into s is 2 by 3. So 2 by 3 plus 2 by 3 minus 1 by 2, that is s plus s minus 1 by 2. Okay, so we can compare. So now this will actually give you something of the order 6.5. So we are very close to what the error which we expected to give. So then here is another problem which you could look at, and then compare again by doing this kind of an evaluation. So notice that you can enter again in this particular example we had x4 as our thing, because our data point which we want to get the derivative was between x4 and x5. So we entered at x4 and constructed a linear polynomial, and then we went to x6 to construct the second order polynomial. You could also do that by going backwards. Okay, that is, you could do x3 and x4, x5, and then construct a second order polynomial, and then look at this error again. Okay, that is, compare that value, the second order, the derivative you get from the second order polynomial of this form by making I as 3. Okay. So we had 4, and then we went to took 4, 5, and 6 points to construct this thing, but we could make it 3, 4, and 5. Okay, so you have first enter it 4, I equal to 4, and use a linear polynomial, and then enter at 3 and construct a quadratic polynomial, and then again compare the derivatives and see what you get, how much error you get. Okay, so please note this function, a similar one, another function f of x will x log x. Okay, and then you could again construct a difference table, take h as 0.3 for example, and then between 1 and 4 you construct that difference table and write a program to do this, and then use evaluate the derivative at x equal to 2.5 for example, using polynomials of different order. Okay, and then look at the error in the polynomial. Okay, so going to the next part. Okay, so we are used to, when doing numerical differentiation, we are used to a formula called a difference formula. that is converting the operator of this form, that is d by dx of some function, okay, into a discrete form. This is a continuous form. Okay, so if Pn of x is a continuous function, and then we can write d by dx of Pn of x. So now when you have a case of discrete, when if this is evaluated given only at some set of discrete points, or you want to write a computer program to evaluate this thing. Okay, one way is, but as we just saw, is to construct a polynomial and then take the derivative. Okay, or another way to do that is to convert this function here, that is that this operator d by dx into itself into a difference formula. Okay, so there are two things which you can do. Okay, one is to say that I take my set of discrete points, okay, which I have, my discrete data points I have. Okay, I will make that into a continuous function by getting an interpolating polynomial, and I take the derivative of that function at any point I want. And so that's maybe the best thing to do if you want to evaluate derivatives at in between points. That means you are given a set of tabulated points, but you want to evaluate derivatives at points in between the tabulated points, and then you need to do something like this. Okay. But suppose you want to evaluate the derivatives only at the tabulated points, okay, then there is another form method available, and that would be to say that I will write this whole operation of derivative itself as a discrete operation. Okay. So that is, I will make it into a discrete formula. Right. So I will not construct a polynomial, but instead of that I will just make this into a discrete formula. Okay. And that can be done only when we are evaluating this derivatives at a tabulated point. Okay. That is d by dx of f at a point x equal to xi. Okay. So if you want to evaluate the derivative of this function at any of these tabulated points, okay, then you could also do that, okay, by making this whole thing into a discrete formula. Okay, the whole process of taking the derivative into a discrete formula. Okay, that's what we see here. Okay. So notice that when we enter at any of the points which are tabulated. When we enter at any of the points which are tabulated, now let us go back here and then look at it. This is our whole form. Okay, we have the polynomial, and then there is the s in terms of s, where s is x minus xi by h. So now if you want to evaluate this polynomial at any of the tabulated points xi, okay, and then the s would go to 0, right, because xi minus xi by h will go to 0. Okay. So that is, if I want to evaluate the derivative of this set of data points given to me, okay, at let us say x2, okay, I want to find the derivative of this function at x2, and I enter the difference table at x2, okay, and then my s is 0, right. So that is s is 0. I enter at x2 and I want to evaluate the derivative at x2. So Pn of xi here would be having s equal to 0, right. So that's the point. Okay. So the function here would simply the derivative for this would be simply Pn of xi is just f of I. That's the way we have constructed the thing. That will be obvious. Okay. But then what will be the derivative? So that is what question is. What is Pn prime of xi, okay, at xi? So that would be s equal to 0, right? At s equal to 0, so that would be 1 over h delta fi plus minus del 2 fi by 2 etc. Okay. So we have non-zero terms, of course, in the derivatives of this problem. So that's what one formula is. So that gives us one formula. Okay. So we just take this, okay, and then I can write it in this form. Okay. The full expansion would be something like this. Okay. So what I have done is I want to evaluate the derivative, okay, of the polynomial, okay, of the set of data points, okay, at one of the tabulated points, and I enter the difference table at that particular tabulated point, okay, and then I get s equal to 0. Okay. And then I can write my derivative as 1 over h delta fi minus del 2 fi by 2 plus del 3 fi by 3 etc. up to minus 1 to the power. So, we are alternating plus and minus sign, and then we have minus 1 to the power n minus 1 del n fi by n. And the error again is of the order of the next term, which would be of this form. Okay. So, it will be delta n power n plus 1 fi by n plus 1. Okay. So, let us look at this in the case of a second order derivative. If I take this by a second order polynomial, okay, so it is basically I say that I terminate this at here, okay, and I just take only these two terms, okay, then what do I get? Okay, so that's the point. So, we just delta fi, and then we have minus 1 by 2 del 2 fi, okay, and del 2 fi is delta x2 x1 minus delta x1 x0, right. So, that's a different further differences. Okay. So, I can substitute for this into this table, okay, and then I would get, okay, f prime of xi as if I substitute for delta fi. So, let me write this here. Maybe. What I am saying is that I can write my derivative Pn prime of xi as using order 2 polynomial, then I will get it as 1 over h into delta fi minus del 2 fi. That is what I would get, del 2 fi, okay, del 2 fi by 2, sorry. Okay, I just put s equal to 0, and then I will get s equal to 0, then I get del 2 fi by 2. So, now what is delta fi? So, we know delta fi is f of xi plus 1 minus f of xi. Now, del 2 fi, that is at I, would be f of xi plus 2 minus f of xi plus 1, right, minus f of xi plus 1. So, that is one term, and this is the difference of the difference, that is f of xi. That is what I would get, right. Okay, so, I can substitute these things into this equation, okay, and then write p2 prime of x into the form given here. That is what is given here. Okay, so, I can substitute for del fi 2 and del fi, and then I will get it as 1 over 2 h plus 4 f of xi plus 1 minus 3 f of xi minus f of xi plus 2, and I have an order of h square error in this. Okay, so, what is this thing that here is a formula. Now, given some xi's set of tabulated points, I want to find the derivative of the function at xi, and I could just simply use this formula, okay, and this only involves points which are beyond xi. That is xi, if I want to find the derivative at xi, I have to use the function values at xi plus 1 and at xi plus 2, okay, and hence this is called a forward difference formula. Here is a forward difference formula, what we normally known as, okay. So, which actually comes from this polynomial interpolation idea for equidistant points, okay. Say that if I want to evaluate the derivative of a function at a given tabulated point, okay, then I can use a 3, or in this case 2, in this case 3 function values at some points which are above or which is after xi, that is xi plus 1 and xi plus 2, okay, and then I can write the formula as 4 f of xi plus 1 minus 3 f of xi minus f of xi plus 2 by 2h. Okay. So, that is a formula which we can write. Okay. So, now a simpler form would be, which is most commonly used, is just use a first order term, that is just f of xi plus 1 minus f of xi divided by h as the derivative at that point. Okay. So, now these are called difference formulas. Okay. We will use this when we are actually solving the differential equations, especially when you are doing the partial differential equations. Okay. We will to convert a continuous differential equation into a set of discrete equations, we will have to write down all our derivatives in a discrete form, and that is what it would be. So, now we can write this df of xi by dx df by dx at x equal to xi as a discrete formula. Okay, that is something which we can use in the future thing. Okay. So now to evaluate the derivative xi, we can also do another thing, and that is to enter at xi minus 1. As I said, we need not. So this formula which we obtained here is by entering, is to evaluate at xi, the derivative at xi, by entering at I. Okay, so we could say that I don't want to enter at I will enter at I minus 1. Okay, and then again use two terms. So this will be delta fi minus 1 plus delta del 2 fi minus 1 by 2. Okay, I can do that. Okay, and then I can then you will find that if I do that I minus 1, and then my s will now. Okay, so if I enter at I minus 1. Okay, so if I take at I minus 1, so then s would be x minus xi minus 1, right? That's what I will have. Okay, x minus x minus xi minus 1, x is xi, okay, divided by h. So now that must be 1. Okay, so if you enter at I, s is 0, and if I enter at I minus 1, s is 1. Okay, so then if you do that, okay, s is equal to 1. If I enter, then I will get my forward difference formula. My difference formula, sorry, not forward difference formula is in a slightly different form. Okay, I substitute for that here, and then I will get my f prime of xi as 1 over h fi plus 1 minus f of I minus 1 by 2. Now this is another difference formula, and this is known as the symmetric difference formula. Okay, so we had a forward difference formula and we have a symmetric difference formula. Notice that here only two values of the functions are used, and we have order h square accuracy, while in the earlier case we had to get order h square accuracy, we had used three values of the function at three different values. Okay, so that is the difference between these two formulas, but both of them are the order h square. Okay, so we will look at higher order derivatives in the using the similar ideas in the next class.